Hello, my name is Thais Arslanbekov, and this is my lab report for Lab 4, a macroscopic view of DC and RC circuits. Here's an introduction to the concepts of this lab. The loop and node rules for circuits allow for the calculation of current through a circuit via solving a system of linear equations. Ohm's law establishes the relationship between voltage, current, and resistance. Charge conservation ensures that no charge leaves the circuit and that is constant in the system. In DC circuits with capacitors, the current is in the same direction, but the magnitude varies throughout. An RC circuit is a capacitor and a resistor connected in series where current is not constant and changes in time. This lab examines different circuit components in different configurations when they are connected in series or in parallel. Here are the formulaic definitions of the previous concepts. Ohm's law followed by the loop and node rules, the potential difference of a capacitor, the capacitance of a capacitor, and a method of calculating R times C in order to compare experimental results with calculated ones in order to determine the effectiveness of the model. In our first model, we have a circuit consisting of two resistors connected in series with 2 ammeters and 2 batteries. The current read in ammeters is the same magnitude, specifically 0.02 amps, a value which does not change even if they were connected backwards. The potential difference is 3 volts. The sum of the potential differences across the circuit would be 0, according to the loop rule. Here's a diagram that tracks the potential difference across different points. The batteries increase the potential, but the wires do not affect it since they are assumed to be ideal, so they do not have any resistance. The resistors lower the potential since they do have resistance, and the 100 ohm resistor lowers the potential a lot faster than the 47 ohm resistor, until the potential reaches 0. The ammeter is assumed to be 0 because it is ideal, so it has a negligible effect. To answer some key questions, the ammeter's reading does not change because the voltmeter already has an incredibly high resistance, so very little current flows in the rest of the circuit, so the reading produced would be negligible. If an ammeter is connected in parallel with a 100 ohm resistor, then both of them will read 0.06 amps because they are in parallel. Here are the calculations performed using Ohm's law, which establishes that voltage equals current times resistance. As for RC circuits, when a battery is connected in series to an RC circuit, the light in the circuit becomes very bright rapidly and then dims slowly until it becomes completely turned off. When it is connected in series with a capacitor, the same thing happens. It becomes very bright really fast, and then it dims until it turns off ultimately. For both of these cases, the current is very large initially, and then it gradually decreases until it becomes 0, which is why the light goes through the same process as the current, because the light is affected by the flow of electrons, which is the current. With a bulb of 10 ohm resistance, it takes about 9.5 seconds to discharge, whereas if the resistance is twice as large and the bulb is 20 ohms, the time also is approximately double, 18.2 seconds. For this RC circuit consisting of a 9-volt battery, a 200 millifarad capacitor, and a 30 ohm light bulb, the voltage was monitored in 1-second intervals for 20 seconds. The voltage versus time produces an exponentially decreasing graph, whereas the natural logarithm of this yields a very linearly decreasing graph. Using the given lab-specific formula, the slope equals the negative of the reciprocal of R times C. Looking at the graph representing the logarithm of voltage versus the initial voltage versus time, the slope is negative 0.171. Plugging this into the formula yields a value of 5.848 for the magnitude of R times C, which is relatively close to a value given from the experimental details, which is 6, so therefore the experiment produces good results. In our idealized simulation, the ammeter has no resistance whatsoever, which is clearly impossible in real life, since even the best real ammeters have some degree of resistance. By having an unideal ammeter contributing resistance, the total flow of electrons throughout the circuit is decreased, and therefore the current is also decreased. Therefore, if the experiment was carried out in real life rather than through a simulation, the values of measured current would be smaller. If we were using a real battery to charge a real capacitor without a resistor, our ideal model would predict that the capacitor would be charged instantly, since we assume there's no resistance in the wires in the batteries. So the theoretical current would be infinitely large and would pass really fast. Since there's always some degree of resistance in real life, it would not be charged instantly, but nevertheless quite quickly. Thank you so much and have a great rest of your day.